All right, so welcome to the deck dive. Today, we're going to be diving into breadth-first search and topological sorting algorithms.
Sounds good.
And you've been kind enough to share with us some of your notes and some code examples in a PDF titled BFS and Top-Level Sorting.pdf,
Yes.
all written in Chinese,
Mm-hmm.
which is quite a challenge.
Yeah,
But the core concepts of these algorithms are universal.
that's right.
We're going to break down these powerful tools, even if the language might seem a bit intimidating at first.
Yeah, the beauty of algorithms is that they transcend language barriers.
Right.
It's all about the structure and the steps.
Totally. So let's start with breadth-first search, or BFS for short.
Okay.
Think of it as a way to systematically explore a graph or a tree level by level,
Right.
kind of like ripples spreading out from a stone dropped in water.
Yes.
It's a fundamental algorithm with applications in everything from finding the shortest path in a maze to, get this, cracking Sudoku puzzles.
It's true. BFS can be incredibly useful in those scenarios.
Yeah.
If you think of a Sudoku puzzle as a graph,
Okay.
each cell would be a node,
Mm-hmm.
and the possible number placements would be the edges.
Okay.
And BFS would help you explore those possibilities systematically, level by level, until you find a valid solution.
Okay, that's starting to make sense.
Yeah.
But before we get too deep into Sudoku, let's break down how BFS actually works.
Sure.
You mentioned, or your notes mention using a queue.
Yes.
What's the deal with that?
So imagine a line at a ticket counter.
Okay.
First come, first served.
Right.
That's essentially what a queue does in BFS.
Okay.
It helps maintain the order of exploration.
Okay.
So we start at a specific node,
Mm-hmm.
add it to the queue,
Okay.
then visit all of its immediate neighbors and add them to the queue as well.
Okay.
And we continue this process exploring level by level until we've visited all the reachable nodes.
So it's like a systematic wave of exploration,
Right.
using that queue to keep track of where we need to go next.
Exactly.
Your notes even have some Python code for implementing this queue. Yes.
Using the collections.deque function.
Yeah, collection.start.deque is perfect for implementing a queue
Okay.
because it allows for efficient addition and removal of elements from both ends.
Oh, God.
This is crucial for BFS, as we need to quickly add new nodes to the back of the queue
Mm-hmm.
and remove the nodes from the front for processing.
I see.
And you can see here in the code, you provided, there's a line that says queue collections.deque start node.
Okay.
That's the initialization step where we create the queue and add the first node.
Interesting.
Yeah.
So we're seeing the code come to life here, reflecting those ripples of exploration.
Mm-hmm.
But why is this systematic level-by-level approach so valuable? Your notes mention finding shortest paths, counting islands, even solving those Sudoku puzzles we talked about.
Right.
It seems like BFS has quite a range.
It does. Think of a maze.
Okay.
BFS helps you find the exit in the fewest steps possible because it explores all paths the same length before moving to longer ones.
Right.
Or imagine a map with scattered islands. Okay.
BFS can tell you how many distinct islands there are
Wow.
by systematically exploring connected land masses.
So BFS is like this multi-purpose tool for navigating and analyzing connective structures. But how does it actually work in practice? I see you've got a code example here
Yes.
for something called level order traversal of a binary tree using BFS.
Okay.
Let's dig into that a bit.
Sure.
What exactly is a binary tree?
So a binary tree is a hierarchical data structure where each node can have at most two children, a left child and a right child.
Okay.
Now, traversing a binary tree in level order means visiting the nodes level by level, from left to right.
Okay.
Imagine looking at a family tree, starting at the top and moving down each generation systematically.
Okay, the visual analogy helps,
Yes.
but how does the code actually accomplish this?
Well, you'll notice that we start by initializing our queue with the root of the tree. That's the topmost node.
Right.
Then we enter a loop that continues as long as the queue isn't empty. Here's the key part. Inside the loop, we process each node at the current level. The line for node in current level is where the magic happens.
Okay.
We're iterating through each node at the current level, removing them from the queue one by one.
Okay, so we're systematically taking nodes off the front of the queue
Yes.
and processing them. But
Mark.
what does processing a node actually involve in this context?
So processing a node in level order traversal means doing something with it, like printing its value or adding it to a list to represent the traversal order.
Okay.
And crucially, as we process each node, we also add its children to the back of the queue.
Okay.
This ensures that we explore level by level, visiting all nodes at a given depth before moving down to the next level.
Ah, I see.
Yeah,
So by adding the children to the back of the queue, we're essentially setting them up for exploration in the next round of the loop.
exactly.
It's like we're creating those neat waves of exploration through the tree. So this is a much clearer picture of how the code translates those ripples we talked about into action.
Exactly, and that's the core of BFS.
Okay.
Now, you also mentioned topological sorting.
Yeah.
It's a different kind of beast,
Yeah.
but equally fascinating.
Yeah.
What are your initial thoughts on topological sorting based on what you've seen in the notes?
Well, from what I gather, topological sorting is all about figuring out the right order to do things when some tasks depend on others. Kind of like figuring out the order to take courses where you need to complete certain prerequisites first.
You got it. That's a perfect analogy.
Okay.
We're essentially trying to find a linear ordering of nodes in a directed graph,
Okay.
meaning the connections between nodes have a specific direction,
Right.
such that for every directed edge, the starting node comes before the ending node in the ordering.
Okay, so directed graph is an important term here.
Yes.
It means the connections aren't just lines between nodes, but arrows pointing in a specific direction, indicating dependencies.
Yes.
So we're not just exploring connections, we're trying to find a valid order based on those directed relationships.
You got it.
Okay.
And your notes go on to mention something called in degree,
Right.
which plays a crucial role in topological sorting.
Yeah. In degree sounds a bit technical.
Sure.
Can you break that down for me?
Absolutely. In degree simply refers to the number of incoming edges a node has.
Okay.
In our course analogy, it would be the number of prerequisites a course has.
Okay.
So if advanced calculus requires basic calculus as a prerequisite, then its in degree would be one.
So if a course has multiple prerequisites, its in degree would be higher, right?
Exactly.
The more incoming arrows, the higher the in degree.
Exactly.
Got it.
Yeah.
But how does this in degree concept help us actually sort things?
Well, the key to topological sorting is starting with nodes that have an in degree of 0.
Okay.
That means they have no prerequisites, so they can be completed first.
That makes sense.
Yeah.
Those 0 in degree nodes are like our starting points in the sorting process. What happens next?
So once we've identified and processed those 0 in degree nodes, we remove them from the graph,
Okay.
effectively fulfilling those prerequisites.
Okay.
This, in turn, reduces the in degree of the nodes that depended on them.
So we're not just removing the nodes, we're also updating the in degrees of their dependence.
Right.
Essentially removing those incoming arrows.
Exactly.
I see how this process starts to untangle those dependencies.
Yes.
Do we just keep repeating this process, finding new 0 in degree nodes, and updating their dependence?
We repeat this process, finding new nodes with 0 in degrees, adding them to our sorted list.
Okay.
And we keep going until all nodes have been processed and placed in a valid order that respects those dependencies.
That sounds like a pretty clever way to untangle even the most complex dependency chains.
Yeah.
Hold on.
Yeah.
Your notes suggest that we can use BFS for topological sorting as well.
Right.
How does that work? It seems like we were just talking about using BFS for level-by-level exploration.
It might seem counterintuitive, but BFS can be a very effective mechanism for implementing topological sorting.
Okay.
Remember how we talked about using a queue in BFS?
Yes.
Well, that queue can also help us maintain the order of processing nodes based on their dependencies.
Okay.
Those in degrees we just discussed.
That's really interesting.
Yeah.
So instead of using the queue to explore levels in a tree,
Right.
we can use it to prioritize nodes based on their in degree.
Exactly.
We start with the 0 in degree nodes, process them,
Right.
update their dependence, and then add those newly 0 in degree nodes to the queue.
Exactly.
And so on. It's
Yeah.
like we're using the queue to manage the flow of the sorting process.
Precisely. It's a clever way to leverage the same underlying mechanism, the queue in BFS, for two seemingly different tasks: level-by-level exploration
Okay.
and dependency-based sorting.
Okay. This is a real aha moment for me.
Yeah.
It's fascinating how BFS can be so versatile. It's not just about those pretty ripples anymore. It's a powerful tool with applications in both exploration and sorting.
And it's not just theoretical.
Right.
Your notes provide a code example for the course scheduling problem using BFS.
Oh, right.
It illustrates how these concepts translate into actual code.
The code uses a dictionary to represent the graph
Yes.
and an in-degree array to keep track of prerequisites.
Exactly.
This is where the real problem-solving magic comes in. Can you walk us through the logic of the BFS algorithm in the context of this code example?
Absolutely.
Okay.
We start by initializing our queue with those zero-degree courses, the ones with no prerequisites.
Okay.
Then, as we process each course from the queue, we remove its corresponding edges from the graph,
Okay.
effectively fulfilling its prerequisite role for other courses.
Okay.
This will potentially create new courses with 0 in degrees.
So as we process courses and remove their edges, we might unlock new starting points for the sorting process, essentially adding those newly 0 in degree courses to the back of the queue.
Right.
It's like a chain reaction,
Yeah,
creating this cascade of sorting as dependencies get resolved.
exactly.
And by the time the queue is empty,
Mm.
we have a nicely ordered list of courses that respects all those prerequisite relationships.
That's right.
This is all starting to click for me.
Good.
But what about those real-world applications you mentioned earlier? We talked about finding shortest paths and counting islands.
Right?
Can you give me some more concrete examples from your notes about how these algorithms are actually used in practice?
Of course. Your notes, for instance, have an example involving a grid of oranges.
Okay.
It's called the rotting oranges problem.
Right.
Imagine you have a crate of oranges,
Okay.
some fresh, some rotten, and every minute any fresh orange adjacent to a rotten one also becomes rotten.
Okay, that's a pretty vivid image.
Yes.
So how does BFS help us with rotten oranges?
Well, we can model the rotting process using BFS. The rotten oranges become our starting points in the queue,
Okay.
and each level of exploration represents a minute passing.
So we're essentially simulating the spread of rot over time,
Exactly.
using the queue to keep track of which oranges are rotting in each minute,
Precisely.
and by tracking the number of levels it takes for all the fresh oranges to rot,
Right.
we can determine the minimum time for the entire crate to become rotten.
Yes.
That's such a clever way to apply BFS.
Yeah, it's like watching a time lapse of the rotting process unfold right before your eyes.
Are there any other interesting applications of BFS in your notes?
There's one about finding the right side view of a binary tree.
Okay.
Imagine you're standing to the right of the tree and can only see the nodes on the rightmost edge of each level, from top to bottom.
Okay, I can visualize that.
Huh?
So how does BFS help us get that view?
We use BFS to traverse the tree level by level, just like we did before.
Okay.
But the key here is that for each level, we only add the rightmost node we encounter to our result list.
So we're picking out that last node on each level, essentially capturing the rightmost edge of the tree as we explore downwards.
Exactly.
That makes a lot of sense.
Yeah,
It's amazing how BFS can be adapted to solve such a variety of problems.
exactly. And there are many more examples in your notes, like using BFS to solve maze problem.
Oh, wow.
Determine if a ball can reach a destination with specific movement rules, and even handle scenarios involving walls and gates.
This is making me realize that BFS is everywhere.
It is.
It's in the way traffic flows through a city, how rumors spread through a social network, even how heat diffuses through a metal plate.
It's a fundamental concept that helps us understand and model a wide range of phenomena.
And don't forget about topological sorting.
Yes.
I'm starting to see how that's present in the way we organize our tasks, the dependencies in software projects, even the steps in a complex recipe.
Exactly. It helps us bring order to seemingly chaotic systems.
This has been an eye-opening deep dive into BFS and topological sorting.
Yes.
But before we move on, there's another algorithm mentioned in your notes that I'd love to explore. Dijkstra's algorithm.
Okay.
What exactly is it, and how does it relate to what we've been discussing?
Dijkstra's algorithm is a powerful algorithm for finding the shortest path in a weighted graph.
Oh, okay.
It's a more general version of BFS, capable of handling cases where the cost of traversing an edge is not uniform.
Okay, so it's like finding the shortest route on a map, where different roads have different speed limits or traffic conditions.
Exactly.
Instead of just counting steps, we're considering the actual cost of each step.
You got it. Dijkstra's algorithm takes into account those edge weights, those costs, and uses a priority queue to prioritize nodes based on their cumulative distance from the starting point.
So it's like BFS with a turbocharger, capable of navigating more complex scenarios where costs and distances matter.
Precisely. And it has applications in everything from GPS navigation systems to network routing protocols.
Wow, this deep dive is really expanding my understanding of algorithms and their real-world relevance.
Yeah.
Your notes even have a specific example of Dijkstra's algorithm applied to network delay time.
Right.
Can you tell me more about that?
Certainly. Imagine you have a network of nodes, like computers or servers, and you want to send a signal from one node to all the others.
Okay.
The network delay time is the total time it takes for the signal to reach all nodes.
Yeah.
Dijkstra's algorithm can help us find the minimum delay time
Okay.
by finding the shortest path from the source node to all other nodes, considering the travel times along each edge.
So it's essentially finding the most efficient way to spread information through a network,
Exactly.
taking into account the varying transmission times between nodes.
Precisely. It's crucial in real-world networks where those transmission times can differ significantly.
That makes sense.
Yeah.
So Dijkstra's algorithm is like a master planner for network communication,
Hmm.
finding the most efficient routes for data to travel.
Exactly.
Your notes also mention an example involving finding the cheapest flight within a certain number of stops.
It is.
Is that another application of Dijkstra's algorithm?
It is. Imagine a network of cities connected by flights with varying prices.
Okay.
We want to find the cheapest flight path from one city to another,
Mm-hmm.
but we might also have a constraint on the maximum number of stops allowed.
Okay, that sounds like a real-world problem that many travelers face.
Right.
How does Dijkstra's algorithm help us find that cheapest flight path?
We use a priority queue to prioritize flights based on both their price and the number of stops they involve.
Okay.
Starting at our source city, we explore outwards, always choosing the cheapest flight with the fewest stops to reach a new city.
So it's like we're building a tree of possible flight paths,
Mm,
but we're always choosing the most promising branches based on both cost and the number of stops.
you got it. And by keeping track of the best prices we've found so far for each city and number of stops,
Okay.
we can avoid exploring unnecessary paths,
Mm-hmm.
making the process more efficient.
That's clever. It's like having a super smart travel agent working behind the scenes, finding us the best deals while staying within our constraints.
Exactly.
This whole deep dive has been incredibly enlightening.
Good.
I'm starting to see connections between all sorts of things now.
That's the beauty of learning.
Right.
It opens up your understanding of how seemingly different things are interconnected.
Speaking of connections, we've talked a lot about BFS, Dijkstra's algorithm,
Mhm.
and their fascinating applications.
Yes.
But I want to circle back to topological sorting for a moment.
Okay.
Are there any more real-world examples from your notes that showcase the power of topological sorting?
Absolutely. Your notes highlight how topological sorting is frequently used in project management for task scheduling.
Okay, that makes sense.
Yeah.
You have a project with numerous tasks, some of which depend on others being completed first.
Mm-hmm.
Topological sorting can help determine the optimal order to tackle those tasks, ensuring all dependencies are met.
Precisely. It's like creating a to-do list that actually makes sense, right? And guarantees you won't hit any roadblocks due to unmet dependencies.
That's a great analogy. It's like having a project manager built into the algorithm itself,
Right.
ensuring everything gets done in the right order.
Exactly.
And I remember from your notes that topological sorting is also crucial in software development for managing dependencies between software packages.
Absolutely. That's another key application.
Right.
You need to make sure you install core libraries before the applications that depend on them.
Right. And this applies not just to installation,
Mm-hmm.
but also to building and compiling software.
Exactly.
Everything needs to happen in the right order.
Precisely. Topological sorting helps us make sense of those complex dependency chains and ensures everything is done in a way that respects those relationships.
So it's like the ultimate organizer for intricate systems,
Exactly.
guaranteeing a seamless flow of processes and tasks.
It's all about bringing order to potential chaos.
This deep dive has been truly mind-blowing. I've learned so much about BFS, topological sorting, and Dijkstra's algorithm.
Good.
And I can't wait to explore even more of this fascinating world of algorithms.
There's always more to learn. The beauty of algorithms is that they're constantly evolving with new ones being developed
Right.
and existing ones being refined to tackle ever more complex challenges.
That's what makes this field so exciting.
Mm-hmm.
It's a constant process of discovery and innovation,
Yes.
finding new ways to solve problems and optimize systems. And it's not just about the technical aspects, as we discussed earlier. The ethical considerations surrounding algorithms are becoming increasingly important.
Ah, that's a crucial topic.
Yeah.
As algorithms become more sophisticated and integrated into our lives,
Yeah.
it's essential to think critically about their potential impact
Mm-hmm.
and ensure they're being used responsibly and fairly.
Exactly. It's not just about the technical aspects of algorithms,
Right.
but also about their social and ethical implications. Your notes touch upon some of these considerations, mentioning concerns about bias, fairness, and transparency in algorithmic decision-making.
That's right. As algorithms are increasingly used to make decisions that affect people's lives,
Right.
such as loan approvals, job applications,
Mm-hmm.
and even criminal justice sentencing.
Wow.
It's crucial to ensure that these algorithms are not perpetuating existing biases
Right,
or
yeah.
creating new forms of inequality.
Absolutely. It's not enough to simply develop algorithms that are technically sound.
Right.
We also need to be mindful of their potential societal impact and ensure they align with our values of fairness, justice, and equity.
Precisely. It's a complex and evolving field.
Yeah.
But it's essential to have these conversations and strive to develop and deploy algorithms that are not only effective, but also ethical and responsible.
This is a great reminder that algorithms are not just abstract concepts or lines of code. They have real-world consequences, and it's our responsibility to ensure that they're used for good.
Well said. As we delve deeper into the world of algorithms,
Yeah.
it's essential to keep these ethical considerations in mind.
This has been a truly insightful start to our deep dive, exploring not only the technical intricacies of algorithms, but also their potential impact on society.
Right.
But before we move on to the next part,
Okay.
I want to leave you with a thought-provoking question.
Oh, well, ears.
Given everything we've discussed about algorithms and their applications, what are your thoughts on the potential for algorithms to both solve problems and create new ones? Can you think of any examples from your notes that illustrate this duality?
That's an excellent question,
Yeah.
and one that deserves careful consideration.
Yeah.
While algorithms have immense potential for good, it's crucial to acknowledge that they can also have unintended consequences or be used for purposes that are not aligned with our values.
That's right.
It's like any powerful tool.
Yeah.
Algorithms can be used for both constructive and destructive purposes.
Right.
It's up to us as developers, researchers, and users of technology to ensure that these powerful tools are wielded responsibly and ethically.
Precisely. As we continue our deep dive,
Yes.
it's important to keep these ethical considerations at the forefront of our minds
Mm-hmm.
and strive to develop and utilize algorithms that benefit society as a whole.
Well said.
This has been an incredibly thought-provoking start to our exploration of algorithms.
Yes.
Stay tuned for part 2, where we'll delve even deeper into the fascinating world of algorithms and their applications.
I'm looking forward to continuing our deep dive.
Until next time, keep exploring, keep questioning, and keep learning.
Welcome back to the deep dive. We're continuing our exploration of algorithms, and in this part, we'll be delving deeper in some specific examples from your BFS and Topological sorting.pdf notes,
Sounds good.
exploring both the technical details and the potential ethical considerations that
Right.
come into play.
We've laid a good foundation, and now it's time to see how these algorithms work in practice.
Yeah, it's one thing to understand the concepts, but seeing them applied to real-world problems can be truly illuminating.
Exactly.
So let's jump right in.
Okay.
One example that caught my eye in your notes was the walls and gates problem.
Okay.
It sounds a bit like a video game scenario.
It does.
Can you set the scene for us?
Imagine you have a room represented as a grid
Okay.
with walls, gates, and empty spaces.
Okay.
The goal is to figure out the shortest distance from each empty space to the nearest gate.
Okay.
It's like you're trying to escape a maze, but there are multiple exits.
Okay, I can picture that.
Yeah.
It sounds like a more complex version of a typical maze-solving problem.
Right.
And I see in your notes that BFS comes to the rescue once again.
It does.
But how do we adapt BFS to handle the scenario with multiple starting points, those gates?
That's the key difference.
Okay.
Instead of starting BFS from a single point, we initialize our queue with the locations of all the gates.
Oh.
It's like we're starting multiple escape routes simultaneously,
Yeah.
with each gate acting as a starting point for exploration.
So we're essentially running multiple BFS explorations in parallel, with each wave emanating from a different gate.
Exactly.
What happens next? How do we determine those shortest distances?
As we explore outwards, level by level from each gate,
Okay.
we mark the distance from each empty space to the nearest gate.
Mm-hmm.
The first time we encounter an empty space, we know that's the shortest distance
Right.
because we're exploring in a breadth-first manner.
I see. So we're exploiting the level-by-level nature of BFS to guarantee that the first time we reach an empty space, it's via the shortest possible route from one of the gates.
Exactly.
It's like those waves of exploration are racing to reach each empty space, and the first one there wins.
Exactly. And because we've started from all gates simultaneously,
Right.
we can be confident that we've found the true shortest distance for every empty space in the room.
That's a clever way to adapt BFS to handle multiple starting points.
Yeah.
It's like a synchronized escape plan, ensuring that no matter where you start in the room, you'll find the fastest route to freedom.
Your notes also mention an example involving a ball rolling in a maze.
Yes.
It sounds a bit more dynamic than our previous examples.
It is?
Can you tell me more about it?
Certainly. Imagine a maze where a ball keeps rolling in a direction until it hits a wall.
Oh, okay.
The challenge is to determine if the ball, starting from a specific point, can reach a designated destination in the maze.
Okay. I can visualize that.
Hmm.
It's not just about simple grid movements anymore. We have to consider the ball's momentum
Right.
and how it interacts with the walls.
Exactly.
How does BFS help us solve this?
Instead of exploring adjacent cells directly,
Okay.
we explore paths.
Mm-hmm.
We keep moving in a direction until we hit a wall, and only then do we add that stopping point to our queue.
Okay.
It's like we're treating each path segment, from one wall collision to the next, as a single step in our BFS exploration.
Ah, that's clever. So we're adapting BFS to account for the ball's unique movement constraints.
Right.
And I bet that visited set we talked about earlier comes in handy here.
It does.
Preventing us from revisiting the same path multiple times.
Exactly.
And getting stuck in an infinite loop.
You're absolutely right. The visited set helps us keep track of the paths we've already explored, ensuring that our BFS exploration remains efficient and doesn't get bogged down in redundant calculations.
It's all starting to come together.
Right.
It seems like a lot of problem solving with algorithms involves understanding the core principles and then creatively adapting them to fit the specific constraints of the problem at hand.
Exactly. It's like having a toolbox full of powerful tools.
Right.
You just need to know which tool to use and how to modify it to fit the task at hand.
And speaking of tools,
Yeah.
your notes delve into a particularly powerful one, Dijkstra's algorithm.
Okay.
Remember how we talked about it as a supercharged version of BFS for weighted graphs?
Yes, it's like BFS, but with an added dimension of cost or distance.
Right. Instead of just counting steps, we're considering the weight of each edge.
Percent. And your notes provide a fascinating example of how Dijkstra's algorithm is used to calculate network delay time.
Okay.
Imagine a network of nodes like computers or servers, and you want to send a signal from one node to all the others.
Okay.
The network delay time is the total time it takes for the signal to reach all nodes.
Okay.
Dijkstra's algorithm can help us find the minimum delay time
Okay.
by finding the shortest path from the source node to all other nodes, considering the travel times along each edge, those weights we talked about.
So it's like finding the most efficient way to disseminate information through a network,
Exactly.
taking into account the varying transmission times between nodes, those edge weights.
Precisely. It's crucial in real-world networks where transmission times can differ significantly due to factors like distance, bandwidth, and network congestion.
This is making me realize that Dijkstra's algorithm is like a master planner for network communication, finding the fastest routes for data to travel and ensuring efficient information flow. Your notes also mention an example involving finding the cheapest flight within a certain number of stops.
It is.
Is that another application of Dijkstra's algorithm?
It is.
Yeah.
Imagine a network of cities connected by flights with varying prices.
Okay.
We want to find the cheapest flight path from one city to another, but we might also have a constraint on the maximum number of stops we're willing to make.
Okay, that sounds like a real-world problem that many travelers face.
Right.
How does Dijkstra's algorithm help us find that cheapest flight path?
We use a priority queue, but this time we prioritize flights based on both their price and the number of stops they involve.
Okay.
Starting at our source city, we explore outwards, always opting for the cheapest flight with the fewest stops to reach a new city.
So it's like we're strategically navigating this network of flight options, always choosing the most economical and convenient route to reach our destination.
Exactly. And by keeping track of the best prices we've encountered for each city and the number of stops to get there, we can avoid wasting time exploring unnecessarily expensive or lengthy routes.
That's impressive. It's like having a super savvy travel agent working behind the scenes, finding us the best deals while keeping our travel preferences in mind.
Precisely. And that's just one example of how Dijkstra's algorithm can be applied to real-world scenarios.
This whole deep dive has been incredibly enlightening.
Yeah.
I'm starting to see how algorithms are the building blocks of so much of our technological world, from simple apps to complex networks.
And understanding them gives you a deeper appreciation for how things work, from recommending products to routing data packets across the internet.
Speaking of complex systems,
Yes.
we've talked a lot about BFS, Dijkstra's algorithm, and their fascinating applications.
Yes.
But I want to circle back to topological sorting for a moment.
Okay.
Are there any more real-world examples from your notes that showcase the power of topological sorting?
Absolutely. Your notes highlight how topological sorting is frequently used in project management for task scheduling.
Okay, that makes sense. You have a complex project with numerous tasks, many of which depend on others being completed first. Topological sorting can help determine the most efficient order to tackle those tasks, making sure all dependencies are met.
Exactly. It's like creating a to-do list that actually makes sense and guarantees you won't run into any roadblocks due to unmet dependencies.
That's a great analogy. It's like having a project manager built into the algorithm itself, ensuring everything gets done in the right order.
Exactly.
And I remember from your notes that topological sorting is also crucial in software development for managing dependencies between software packages.
Absolutely. That's another key application.
Right.
When installing or compiling software, you need to ensure that core libraries are installed or built before the applications that depend on them.
Right. Everything has to happen in the right order to avoid errors or conflicts.
Exactly.
Topological sorting provides that order, ensuring a smooth and error-free process.
Precisely.
Yeah.
It's all about making sense of those complex dependency chains and making sure things are done in a way that respects those relationships.
It's like the ultimate organizer for intricate systems, guaranteeing a seamless flow of processes and tasks.
Exactly. It's all about bringing order to potential chaos.
This deep dive has been truly mind-blowing. I've learned so much about BFS, topological sorting, and Dijkstra's algorithm.
There's always more to learn. The beauty of algorithms is that they're constantly evolving, with new ones being developed and existing ones being refined to tackle ever more complex challenges.
That's what makes this feel so exciting. It's a constant process of discovery and innovation, finding new ways to solve problems and optimize systems.
And it's not just about the technical aspects, as we discussed earlier. The ethical considerations surrounding algorithms are becoming increasingly important.
That's right. It's not enough to develop algorithms that are technically brilliant. We also need to be mindful of their potential impact on society and ensure they're being used responsibly and fairly.
Precisely. It's crucial to have those conversations and strive to develop and deploy algorithms that are not only effective but also ethical and just.
This has been an incredibly insightful journey so far, exploring not only the technical intricacies of algorithms, but also their potential impact on society. But before we wrap up part two,
Okay.
I want to circle back to something you mentioned earlier that really stuck with me, the idea of algorithms as a way to understand the patterns and relationships that govern our world.
Yes. Algorithms provide a framework for breaking down complex problems into manageable steps, revealing the underlying order and structure that might otherwise be hidden.
Exactly. It's not just about code and computation, it's about using these algorithmic tools to gain insights into the world around us.
Precisely. Whether it's understanding how information spreads, optimizing travel routes, or even predicting future trends, algorithms give us a powerful lens through which to analyze and understand complex systems.
This is making me think about how algorithms are present in so many aspects of our daily lives, even if we don't always realize it. From the recommendation algorithms that suggest what to watch or buy online, to the routing algorithms that guide our GPS navigation systems, these algorithms are constantly working behind the scenes to shape our experiences.
You're absolutely right. And as we delve deeper into this deep dive, we'll uncover even more fascinating examples of how algorithms influence our lives, often in ways we might not even imagine.
Well, this has been an incredible part two, exploring a range of algorithms and their applications. But before we move on to the final part of our deep dive, I want to leave you with another thought-provoking question.
I'm ready for it.
Given everything we've discussed about algorithms and their applications, what are your thoughts on the balance between efficiency and accuracy in algorithmic design? Can you think of any scenarios from your notes where this trade-off comes into play?
That's a great question. Often in algorithm design, we're faced with a choice. Do we prioritize speed and efficiency? Or do we aim for the most accurate solution, even if it takes longer to compute? The answer often depends on the specific problem we're trying to solve.
That makes sense. Sometimes a quick and dirty solution is good enough, while other times accuracy is paramount, even if it comes at the cost of speed. Your notes mention an example involving image recognition algorithms, right?
Yes, image recognition algorithms are a perfect illustration of this trade-off. If you're building an app to quickly tag photos on social media, a faster but slightly less accurate algorithm might be acceptable. But if you're developing an algorithm for medical diagnosis where accuracy is critical, you might be willing to sacrifice some speed for a more reliable result.
That's a great example. It highlights how the context and the stakes involved can influence our choices when designing and implementing algorithms.
Exactly. There's no one-size-fits-all answer. It's all about understanding the trade-offs and choosing the best approach for the specific problem at hand.
This is a great reminder that algorithm design is not just about finding the right answer, but also about making informed choices that balance competing priorities.
Well said. And as we move into the final part of our deep dive, we'll explore even more nuances of algorithm design and the considerations that go into creating effective and responsible solutions.
I'm looking forward to it. Stay tuned for part 3, where we'll wrap up our exploration of algorithms and their impact on our world. Welcome back to the final part of our deep dive into breadth-first search and topological sorting. We've covered a lot of ground, from the basic mechanics of these algorithms to some pretty fascinating real-world applications. But before we wrap things up, I want to touch on one more crucial aspect: connecting these concepts back to your you and how you can use this knowledge.
Absolutely. It's one thing to understand algorithms in theory, but the real power comes from applying them to solve problems that are relevant to your interests and goals.
Exactly. Remember that PDF you shared with us, BFS and topological sorting.pdf? It's packed with code examples, but those are just starting points. The real challenge and the real fun is figuring out how to adapt these concepts to new situations.
That's where the real learning happens. It's like taking the building blocks we've explored and constructing something entirely new.
Precisely. So let's shift gears and talk about you. What specific challenges are you facing, either in your work or personal projects, where BFS or topological sorting might be helpful? Remember those dependency chains we talked about? Think about areas where you need to figure out the right order to do things, whether it's managing tasks, organizing data, or even planning a complex project.
And don't forget about the exploration aspect of BFS. Are there any scenarios where you need to systematically search through a network, analyze connections, or find the most efficient path? Think about problems involving navigation, data analysis, or even social networks.
Those are great points. It's all about recognizing the patterns we've discussed and applying those algorithmic lenses to your specific needs. For example, if you're working on a project with a complex web of dependencies, topological sorting could help you create a clear roadmap for completing tasks in the right order.
Exactly. And if you're trying to analyze a large network like a social graph or a transportation system, BFS could be your go-to tool for exploring connections, identifying clusters, or finding the shortest paths between points of interest.
The possibilities are truly endless. And remember, you don't have to be a coding wizard to benefit from these concepts. Even a basic understanding of BFS and topological sorting can help you think more strategically about problem solving and decision making.
Absolutely. It's all about having that mental framework, those algorithmic tools in your back pocket, ready to be deployed when the need arises.
So, as we wrap up this deep dive, I want to leave you with a challenge. Take one concept or technique we've discussed and see if you can apply it to a problem in your own life. It could be as simple as using BFS to plan your next road trip, or as complex as implementing a topological sort algorithm to manage your work projects.
And don't be afraid to experiment. The beauty of algorithms is that they can be adapted and customized to fit your specific needs.
Exactly. So go forth, explore, experiment, and see what amazing things you can accomplish with the power of BFS, topological sorting, and the whole world of algorithms at your fingertips.
This has been a truly insightful deep dive. It's been a pleasure exploring these concepts with you.
Thanks for joining us on this algorithmic adventure. Until next time, keep learning, keep exploring, and keep diving deep.